Today, I'm going to talk a little bit about not my current work, but work that I hope to do starting around now. I'm going to start off by talking about where I see the state of the semiconductor industry. And I think we're now entering in the post-Moore's Law age. And I'll explain what I mean there. And I think we have an opportunity to do something a little radical, and I'm going to try to convince you to join my cause. Okay, so the technology landscape is really changing. For over half a century, information technology has been driven by semiconductor technology scaling. And that scaling made computation cheaper. And in fact, the fact that computation will get cheaper, I think, underlies a lot of assumptions we all make implicitly without even thinking about it. And in fact, even before we went to semiconductors, there were tubes, and before tubes, there were mechanical computing devices, and before that, there were relay devices, and then before that, there were mechanical devices. And throughout the entire history of mankind, computing has gotten cheaper and cheaper over time. And I think we're at the end of that S-curve. And that means, unfortunately, that scaling is now broken, and that really affects how we think about future systems and future system design. And with all catastrophes, there are opportunities, and I think we should think about the opportunities that this transition gives us. So, I think this is clear for those of us my age, which I think there are a few of you in the audience. Like, I remember working on, machines you didn't see at terminals, right, and punch cards before that. But I think for most people in the audience, you started out with sort of laptop computers, and we've moved from laptop computers to using mostly cell phones. And, a lot of people are sporting watches that do a lot of the stuff that, the laptops used to do. And so this expectation of computing becoming smaller, more powerful, and cheaper is quite pervasive. In fact, if you think about it, if you're in any field other than computing, and you're doing some sort of computational modeling, you're always making the models more accurate, aka more complicated. And the reason we do that is we assume that the future computing, even if it takes a little too long today, in a few years, it will be okay and it will become mainstream. And in fact, we think that we have to do this because we have this capability that will become available. What are we going to do with it? And the companies like Google and everybody else with the cloud computing have, elastic computing has sort of fostered this thing that now, you can use 1,000 computers without thinking about it. I think the underlying driver of this expectation is Moore's Law. And Moore's Law is many things to many people. It was usually, the computer architecture was talking about the performance of computing increasing. If you talk to Intel, it's talking about the number of transistors, that they're shipping increasing. But if you go back to Gordon Moore's original paper, it was really about the cost per component. I always use twice as many transistors. I just buy 2 chips, right? The whole point of this was, if I look at where the cost optimal point of a transistor is, what Gordon Moore pointed out was that the cost optimal point was increasing, the number of components over here was increasing, and basically that the cost of those points, the optimal points, was decreasing with time. And so what that meant is I got this exponentially increasing number of transistors at ISO cost. Okay? So for me, Moore's Law is all about cost per transistor. Okay, and Gordon also thought cost per transistor was very important, because when he gave a keynote 20 years ago at ISSCC, he basically plotted what the cost of a transistor was over many, many decades. And he showed that on a semi-log plot, it's been exponentially decreasing with time. So to me, Moore's Law is about what I can do with constant dollars. I don't want my laptop to increase exponentially in cost as the performance increases, right? When transistor costs scaled, it was great, because making the same product, if I moved it into a new technology, it basically cost less to make that product because it had constant transistors, and therefore the transistors were cheaper. And what that meant was, from an industry perspective, we always used the most advanced technology for any volume product. And if we had a volume product, we moved it into the advanced technology because it would be cheaper to do, and if we didn't, our competitors would, and we would have a cost disadvantage. Which meant that if you thought about the semiconductor industry, we're always building more of the latest technology. We were never building older technologies. The fabs were, they were there, we used them, but new technology was always what we wanted. And therefore, all the fab development, everything that we tried to do to ramp volumes, were always in the latest technology. Now, I don't know if you've noticed, but I certainly have, that this is no longer the case. AMD made a big point in their Ryzen processors that they have the I/O frame, and the I/O frame in the middle was in the older technology, and the processors were in the newest technology. Well, if the world was as it was, that makes no economic sense. Okay. And assume they're not dumb, so something has changed. And I contend that what has changed is Moore's law has really ended. The cost per transistor is no longer scaling. Now, there was a plot that was given by the CEO of Qualcomm at an ERI summit about 4 years ago, where he surprisingly showed this data, which I didn't think people published data about cost per transistor, but he showed the cost per transistor over time in different technologies. And notice first that this is a linear scale. So that's the first thing, and that's weird. It's usually plotted on a log scale. And the second thing is, the blue line is what the cost per transistor was at introduction. Okay, that's definitely flat or going up. And the red dots are what happens in volume production. And it is true that in volume production, the cost per transistor decreased, but this is on a linear scale, and it's not decreasing very much. Okay, this was in 2019. Okay, so there's not data what's happening recently. So I do what all good researchers do these days. I went to the web, and I Googled, cost of transistor or something. And, I got this data. Now, this is supposedly TSMC data. And I always thought that TSMC data of what costs were highly proprietary. And so, but it was on the web, so we have to assume it's right? Anyhow, what you see is that for 7-nanometer technology, a wafer cost about $10,000. In 3-nanometer technology, the wafer cost doubled. It costs about $20,000. Historically, the wafer costs have been relatively constant as we scale technology. It crept up a little bit. Okay, but you think, okay, not so bad. 7 to 3 is a scaling of a little more than 2, so that squared is 4. So therefore, it's okay. Price doubled, but the number of transistors quadrupled or more, about factor 5. Okay, except notice that the increase that you get from these technology scalings, when you multiply them together, are just a little over than 2. Okay, so since it was on the web and it proved my point, I decided it was absolutely true. I'm sure you would never do anything like that, but anyhow, then I found more data on the web, and this is an amazing website if you haven't seen it. It's basically a person who's been tracking prices per bit of memory in different forms for 70 years. Okay. And what he does is he actually goes on the spot market and just looks at what the cost is. So, this isn't proprietary, this is just data. And once again, what you see is historically, this is again on a semi-log plot, You see exponential decreases in the cost of memory and the cost of disks until you see the last decade where things are definitely flattening out. Okay, so all the data that I have seen indicates that from a cost perspective, scaling transistors, which we are still doing, is not providing us the cost benefit that we used to. This is not good news. Now, when technology scaled a factor of 2 over time, we initially had more in Dennard scaling, and that meant we got more transistors, they got more efficient, they got faster, we were in like hog heaven, it was wonderful. You know, actually, we never really scaled power supplies quite as much as Dennard scaling said we would. So the power did go up, but things were really good. That ended, you know, 15 years ago or more. Now we were in the Moore's law where things still got cheaper. They didn't get that much, gates didn't get that much faster, but they did get a little bit more energy efficient, not quite as much. And that's the reason that you think about Debbie's talk and what happened. You saw the price, the power per chip going up because we're not scaling energy as much when we're scaling more. But now we're in a completely different domain where technology numbers in the terms of scaling aren't really representative of transistor density directly. They are talking about improvements in overall technology. Transistors are not scaling in cost, but energy is still scaling down and the capability that you get is still increasing. But this is a very different world than we were in before. So if you're thinking about what this means, the world still expects computing performance to improve. So if your underlying technology is not intrinsically improving by very much, it is the responsibility of this community and the software community to start delivering the performance gains that the world expects. So that really means that we need to do some sort of specialization or optimizations for the applications because we have to more efficiently implement those applications onto the underlying technology. Okay. Now, generally speaking, what this means is that we're going to increase the product SKUs, the number of unique things that we deliver to the customer. So it used to be, you know, we had one microprocessor. Intel would have the leading edge microprocessor. If you look today, there are all these different variants of the processor for different class markets, and that's because we're trying to optimize everything for particular application classes in order to continue to deliver performance. That in turn means that each of the designs we do has a slightly smaller market than they had before. And we need to decrease the non-recurring engineering costs for each of the different variants of the products that we're building in order to optimize the dollars per function that we're delivering out to the end user. And because we're doing that, we're using different technologies because per square millimeter, new technologies are more expensive, so things are not scaling like IOs and various other things don't scale perfectly, or analog. Leave them in an older technology because it's actually cheaper to do that today. Now, all of these things, you need to have more parts, more products. You want to decrease the cost per product. You want to be able to leverage multiple technologies. Does that sound familiar to anybody? Like, did someone say chiplets? Okay, so oftentimes chiplets are being touted as this great new technology that's going to improve things. I view chiplets as a way of addressing the current dilemma that we face because we need to basically create more variants of products at constant design costs. Now, I should have told you this talk starts off with a bunch of bad news before we get to the good news, but okay. I think chiplets are not the answer. That is, chiplets are an extremely useful technology and we are going to go down this road, But fundamentally, chiplets do not solve the problem of decreasing cost per transistor or anything like that. They're a way that we can do application optimization. But if you think about a chiplet, the problem is, in a chiplet, I have to pay for this base die, right? And then I have to pay for the transistors and the other dies I'm stacking, right? So from a cost per transistor perspective, I'm not changing the cost per transistor. And even worse, if I don't do the vertical chiplets or the 3D chiplets, if I do what most people do, which is basically take the chips and mount them on a planar substrate, then I have to pay for all the transistors, and I have to pay for the substrate. Okay? And the high-density substrates right now are made on silicon, so they're pretty expensive. There's lots of people who are trying to build organic substrates, right, to decrease the cost. But everything's adding dollars. It's not like subtracting dollars. So again, you have the interposer you have to pay for. It does allow different parts of the systems to use different technologies, right? It also allows us to do interesting technologies, incompatible technologies together. So I think if you're a believer in photonics, all photonic systems are basically going to be chiplet related because the optical components are generally not on the same technology that you're going to do in your advanced silicon stuff. All of this is going to happen, and it's going to be useful, and it's going to give us capability we didn't have before, but all of it increases essentially the cost per transistor, right? It doesn't decrease it. So it's our responsibility, once again, to take this new kind of capability and figure out how to generate better end application performance. Okay. So at this point in the talk, I acknowledge we have a problem, right? The world is changing, and we better react to it in some way. So I said that in order to continue to improve the performance, we have to do application optimization. We have to tailor things to particular application classes. So the big question is, who's going to do this application optimization? And the reason this is a dilemma is because we've been so frickin' successful, right? If you think about the microarchitectural community, and the semiconductor technologies, we have leveraged all this advanced technology and the complexity by building ever more complicated machines. So the machines that we're building today are amazingly complicated. I was a person many years ago, before we did out-of-order machines, and I just looked at history and said, every time someone built an out-of-order computer, they never built another one, right? There were many people who built out-of-order computers before we did the Pentium thing, right? And all those companies, the next machine after they did that was basically back in order. And that was because they're so complicated and hard to design that they decided it wasn't worth it. But we have managed that, so all the machines, so I was wrong, and all the machines moving forward are out of order, all the high-performance machines. Okay, but what that means is the base level systems that we're doing are incredibly optimized, and very hard then for a person who just has an idea to actually to create a new piece of silicon. And the result of that, the way it's usually couched, is that designing one of the state-of-the-art systems today costs hundreds of millions of dollars. And what people who look at this realize is that most of the cost is actually not in the hardware design. Most of the cost is building the software, the firmware that makes the hardware work, because everything is programmable today. Excuse me. And then the operating systems and support services that run on top of that platform. It's the systems that we all expect to use when we have a computer are amazingly complete. Okay, because of the complexity of the systems that are basically being shipped today, we have a consolidation in the semiconductor industry. So the number of people building things is going down. And what I notice in academia is the number of students who are interested in kind of the hardware space is decreasing. I mean, and it's not completely irrational. These things are very complicated. There are certain companies that are excellent at it, Apple, Intel, Qualcomm, NVIDIA, okay? But if you're gonna do work in this area, you have to go work at one of these companies that have the teams to build these very complicated systems. Okay, so I go back to the question I asked before. In order to do improvements that are really gonna move the ball, we're gonna have to do some really serious innovation. And, in innovation, most innovative ideas are bad, right? It's like most of them who try crazy things, they're crazy, right? But the few of those crazy ideas actually move the world. So we need to enable lots of people to try crazy ideas to find the ones that are actually gonna change history. So who's gonna do that? So we end up with a paradox. In order to do real application optimization, it requires radical thinking. Most radical thinking requires fresh workers. That's why universities are so good at creating new things. They have a whole bunch of students, and they don't know that all these things are impossible. And because they don't know they're impossible, they just go try to do things. And as Joel said earlier, they question assumptions, or maybe they don't know the assumptions, and they just move forward, and it's great. And if we're smart faculty members, we don't tell them the assumptions, okay? And then they surprise us. But as I said before, most real radical thinking doesn't work. Thank you. Okay, so if we want to engage this, we have to solve this problem. Right? You can't do a lot of radical thinking if every radical experiment costs hundreds of millions of dollars. It's like, I had this joke in another talk where, I have this curve, and if it doesn't cost very much money, it's easy to do. When you start getting to hundreds of millions of dollars, those people want their money back. Right? If they invest in you, they really want their money back. Okay, so they're not gonna do stuff really radical. Okay, so how are we gonna solve this problem? There's only one approach that I can think of, and that is we have to make the task of designing and playing in hardware or doing this hardware-software co-design that we all say we need to do. We need to make it exciting, so it brings in new people. And in order to make it exciting, it has to be cheap enough that people think that they can do something and change the world. So it has to be possible for small teams to accomplish, which seems like it's an impossible task. I just said it's hundreds of millions of dollars, blah, blah, blah. There are not very many advantages of being old, I'll tell you. It beats the alternative, right? But there are some, and one of them is that you have a broader view of history. And so I've seen this rodeo, I've seen this problem once before. When I was a kid, I actually was an IC designer before 1980. I designed my first chip in 78, okay? And during the 80s, there's this amazing revolution that happened, which is called ASICs, right? AKA the way we design all integrated circuits today. But it was not the way we used to design integrated circuits. ASIC design was really a method that allowed people who built logic boards, the logic designers, to create chips. Right? In order to do that, they created many new kinds of CAD tools and design approaches. Standard cells weren't a thing, but in order to represent kind of the base logic gates that they were used to, we created standard cells. We created placers, which were modeled after the placement of the chips on a board, routers to connect the standard cells together, and then synthesis to take some logical description and make it into standard cells. Okay. None of that technology existed before the 80s. And those collections of tools created an enormous new market that enabled a very large group of designers to partake in silicon, to take advantage of silicon. The thing that you might not know is that Synopsys, the synthesis company, wasn't started to do synthesis. It started as a logic optimization company for people doing boards. And took that logic optimization technology and converted it into being able to take a higher level logic description. Verilog was not written to be a synthesis language. Verilog was written to be actually a logic simulation language, and got converted in the process. So this whole set of technology was really built to enable people who didn't understand chip design to do chip design. And I know this as a fact because I was a chip designer, and I'm telling you all the times, you probably know me as some famous person, so you think I was right. So I just told you I was totally wrong about out-of-order computers. I also, at this time, thought ASIC design and tools were stupid because these ASIC designers didn't know all the important things about chip design, about wire delays and capacitance loads and all these things that I, as a chip designer, knew. Okay. So, I was right. They didn't know about all those things. But it turns out over time, the tools got better and better, and the tools started knowing about these things. And so that's how we do chip design today. No chip designer would have used ASIC tools back in the day because they didn't produce very good chips. The point is that the chips they produced were better than the alternative, which is to do the board level design using the chips that we produced. So it didn't matter that they weren't state of the art. What mattered is they allowed a new market to basically do design. Everybody with me? Okay. So because it enabled a bigger group of people to do design, there's a lot of money to make those tools better. And within a decade, all the things that I said the people didn't know, they still didn't know. Well, a few of them knew, they got expertise, but the tools got better and better and started doing all these things in the tool. So in the end, all chip designs are using these tools right now. Okay, this invented the fabless semiconductor market. And most of the chip companies, besides Samsung and Intel, which existed before, are actually ASIC companies that have taken over the market. Okay, so I started off this talk saying we needed a revolution. We needed to think differently about design because we need to enable a group of people to take advantage of this technology to try crazy things. Okay, so how can we do this? How can we redo the 80s? How can we enable a new group of people to take advantage of silicon technology? So I think if you're going to try to create a new market, you should try to answer 4 questions. And for people who know about the Hallmeyer questions from the DARPA things, these are all very similar. You have to say, who are the new designers? That is, who are the people that we're trying to enable to do design? How do they do design now? What abstractions do they use? Because when you want to enable a new market, you're not going to teach the market a different way of thinking. You have to address the market and the way they think. Okay. Then you have to say, they haven't done this in the past. Why are they going to do it now? Right? And then if you can figure out a positive answer to all those questions, then you have to say, how in the heck are we going to get it? How are we going to do this? Right? There's the small problem of how. Okay, so who? Okay, the problem that we're facing right now is we need to do hardware-software code design or hardware-software optimization, right? The underlying technology is not changing. The application has some demand. How do we meet the application's demand with the available technology? And we all say that it's going to be, algorithm hardware code design, right? So who is going to do this algorithm hardware code design? I think it's the people who care about the applications because they understand what the domain they're working in. And from a microarchitecture perspective, I think one of the most important things you can do is find some applications that you care about or find people who care about those applications and work with them. Start with the specific, try to do some things, and then you can try to generalize. Okay, but I think it's application designers. And yes, I mean software people. I'm not talking about us who kind of play in the application space and understand hardware a little bit. I'm really talking about people who care about applications, do that, they ship that for their living. So that's who. What do they do? Okay, they don't have any knowledge of hardware, but I'll decrease the application designers into application designers who care about performance, a much smaller group. Because if you don't care about performance, you're never going to do hardware. Like, that's more complicated. But if you care about performance, okay, then I think you might be interested in doing hardware. And I assume that if you're an application person who cares about performance, you know about two things. You have to know in today's day and age about locality and parallelism. Because there's a lot of threads and cores and SIMD and all this other kind of crap. If you don't know about that, you're not going to actually get performant code, right? So I'm going to assume that they understand performance tuning and they understand about locality and parallelism. Now, this group has never been interested in hardware before. In fact, one of the problems with building customized application-specific hardware is that the people who you want to use your hardware won't talk to you until it's actually shipped, which is totally backwards, right? But they're busy making a product and trying to make money. And if they can't sell it, they don't care about it, right? And so what we need to do is sort of encourage them to care about it. And why are they going to do that now? Well, they're performance tuning their code. The base platforms are not getting better. They're going to be desperate. Like, eventually, tuning their code is going to get so hard, they're going to say, well, maybe I can build something that makes it easier than doing this crazy kinds of stuff that I'm trying to do. So I think this transition, which is bad, is going to encourage people on the software space to become more interested in looking at some hardware issues. And I think hardware-software co-design will become an interesting problem for them. So that leaves me with the final problem, which is how are we going to do this? Which I call is the new design challenge. And I'm going to take an analogy in the cell phone business because I think the major innovation that Apple did when it launched the iPhone was not the keyless flat screen, which was very important, but I think it was the inclusion of an app store and an app API. So in order to enable innovation, I think we have to enable application designers to deliver apps. And that means they are creating an application on a system. They are not creating the system. Okay? Systems are wickedly complicated. I think if you really are going to create your own custom system, there's no way that I know of yet to do that cheaply. And the application designers typically have a platform that they're working on. That's what they're used to dealing with. You start changing that base platform, and it's an enormous amount of work for them to work to a different platform, right? So why don't we just assume that the platform is, and we're going to add incrementally to it. Okay, and I think that's an acknowledgement of two things, is that the software support infrastructure that the application designers are using right now are incredibly complicated, and replicating that is going to be very expensive. And also, the fact that any base system takes a lot of engineering to get working. Now, this is Point of Vecchio, which is one of the most complicated silicon pieces. So, okay, maybe that can't be done cheaply, but I would say even just a modern microprocessor is incredibly complicated to design, and the software that you have to build to actually make it all work is very difficult. So you might say, well, what about open source hardware? I mean, won't open source hardware sort of address some of these issues? Perhaps, and you can make an argument, I can make an argument about how open source hardware could help this, but I think you have to figure out in that thing how to address two big issues. The first is you're still building the system. If I take pieces, open source pieces, and put them together to build a system, I'm still constructing the system. And in my experience, when I build a system out of different pieces, unless somebody else has done it before and so it sort of exists prior, there's a whole bunch of issues that I have to resolve to figure out how these complicated blocks interact correctly. The second thing is if I put the system together, I have to build the software system, the OS and all the software support tools that run on that system. That's also a very big job, unless, of course, it's been done before. But if it's been done before, we're talking about using a platform, okay? Right, and one of the biggest costs is the software development environment, the debuggers and compilers and optimizers, all for the software thing, which again, anybody who's built hardware knows that development arc is longer and more expensive than hardware development. And finally, the other issue, the second issue, is just, in my experience, maintaining systems costs money. It takes people. So in all open source projects, you can point to various companies who pay for that open source development. You know, nothing's really free. And so you have to have an economic argument about who is actually going to pay for the development of this open source and maintenance of this open source hardware. It's not impossible, but if you're talking about it, you should think about who's going to do it, what large organizations have a rationale for paying money to support the system because they want to build things on top of it or something like that. So I think for this revolution, I'm not going to count on open source hardware. Instead, what I'd like to do instead is to get somebody who builds these platforms and sells them to allow us to add little widgets to it, okay? Like Apple sells the phone, but the API for that is basically open. Okay, this base platform has to consist of hardware and software, and it has to consist of these APIs that allow, and the hardware software can be proprietary, I don't care, but the API that allows me to connect into it has to be open. Now, one of the advantages of this model is it creates an open interface for everybody to use while maintaining a proprietary and revenue-generating platform, because I think people need to make money in order to continue to supply things, okay? The other important thing is that this API has to be what I call a zero support interface. And what I mean by that is if the interface doesn't work, it's your problem. It's not me as the supplier of the interface's problem. So Apple has this API and Google has an API. And yes, if it doesn't work, you can file a bug report. But Apple and Google are under no obligation to fix that bug report in any finite period of time. Right? And the reason for that is, remember, the expected return on investment for all the people who are building these apps on my platform is negative. That is, most people who write apps for a phone lose money. They're probably not paying themselves when they create the app, but most apps are not actually successful. And I don't want to have to do support for all those people, because if I did, it would be very expensive. Okay, so I can then support infinite number of users because they don't cost me anything. But to create a good interface does cost money and has to be maintained. Okay, so I'm not saying this is free, but I'm saying I can imagine a model where I can enable, crazy undergraduates or graduate students or researchers at any company. They can use this and play kind of on their time, and that doesn't cost me any money, that's just upside. Because if they do something interesting, I can then later incorporate it in my platform. Okay, so the design CAD problems that we need to solve, the how, is we have to figure out how to transform somebody who thinks about things in terms of software into an actual working piece of hardware. Okay? So there's the hardware-software co-design, which if you're a software person, you think about it as scheduling. How do you schedule the algorithm? How do you repartition the loop structure? How do you block it in various ways? If you're a more micro-architect hardware person, you call it design space exploration. but it's basically how do you rearrange the parts of your algorithm in a way that can take advantage of hardware. And in my view, hardware only gives you three things. It gives you locality exploitation, it gives you vast amounts of parallelism, and it gives you specialization to do whatever ops you want to do as efficiently as possible. Okay. So in this part, I think there's a vast opportunity for microarchitects to figure out how to basically codify some of this stuff and make it work. Then once you have transformed the algorithm into something, you actually need to take that structure, that data flow graph, and map it to hardware. Okay. You also need to create these clean APIs, which abstract many of the hardware issues that the software people won't know but need to be handled. And you need to be able to create efficient implementations to connect your user-level application running in the system to a piece of hardware, which for people who understand OSs and other things is non-trivial. And then, of course, we need to provide validation and debugging support because we have people working at the code level. They're going to connect it up. It's not going to work because connecting to any sufficiently complicated system means you don't understand how the system works. And because it's a zero support interface, you have to give the users tools to basically figure it out. So an explicit non-goal is to help current chip designers. That is, there are many billion-dollar markets, might I say machine learning right now, okay, that have tremendously large design teams that are trying to solve those problems. The initial work, the initial tools are not going to be great. In fact, they're not going to compare to what you can do if you have a 100-person team working on doing something. I do not want to try to build the tools with all the little knobs that you have so you can tweak it to exactly how you want to do it, because then it will make it unusable to somebody who doesn't know what to set all these tools to. Okay? So it's got to work in a restricted space. And so let's focus on enabling people who can't do design initially. I believe if we do that, over time, we will actually embed enough intelligence in this that the world will move to this kind of tool because it will be more efficient. But if we try to do that from day zero, we're going to lose. So let's not try to do it. So as I said, one of the most important steps is hardware-software co-optimization. You need to have the application designer do a design space exploration or explore how to reorient their code. And these are all the things that we do all the time when we are looking at building the papers or writing the papers that we do. How do we exploit locality? How do we exploit parallelism? How do we break dependencies? And the reason I think that it's very important that the application designers do this is that they're the people who know what you can break. These programs will not compute exactly the same answers as the program did before. Because if you try to actually do the same algorithm in an accelerator, it doesn't go very fast. Right? You know, that's the thing that we don't ever talk too much about. We always rewrite the algorithm for our accelerator because we have to, and it computes slightly different things. I think, you know, I know large language models are the thing, and this is the only time I'm going to mention it, but I think the ability of large language models and machine learning has enormous potential in this space to basically apply or be able to suggest various transformations that might be useful to do, and then we have some tools to do that. Once we've done that transformation, then we have to actually convert the code to hardware. There are already tools that do this in terms of high-level synthesis. There are some issues with these tools. They're not great, but I think we have steps to do that. The problem with high-level synthesis, as anybody who's tried to do this knows, is that we don't really want to take an algorithm and build a piece of hardware that does that algorithm. Because algorithms change with time, and we want to be able to map that changed algorithm onto the hardware. So we really want an engine that's optimized for a class of application that I can effectively tune over time. If you think about the requirements for this kind of high-level synthesis, it's actually something that develops both a piece of hardware and a compiler that maps the application to that piece of hardware. It is this tool that doesn't exist in the world. Some of the research that I've been doing at Stanford over the past few years has been looking at how to do this kind of tool. But I think there's a lot of work that can be done here, and I think there's a lot of interesting questions that can be answered. Because what we really want is, given this class of algorithms, build me an engine that basically executes them effectively. And then over time, because I believe the only software that works is software that you've used before, you want to be able to evolve that software system over time. And then we talk about the APIs. I think the APIs can be broken into sort of two classes. There's silicon issues and system issues. Remember, the people that are doing this silicon or doing this hardware have no idea about hardware. So all the stuff that we do in power states and gating, thermal throttling, varying VDD, are things that these designers won't actually know about. So we need to provide them APIs that they can call that do some of these things. The other thing that, that we have to deal with is the fact that actually turning on a piece of hardware is one of the most complicated things that hardware does, right? Nobody thinks about how many processes run when you boot your computer, but it's like 3 or 4 levels of boot that happen, especially in the machines that have secure enclaves, right? So that all has to be thought about and regularized. So there are API calls that do the initialization, right? Just power up sequencing, right? Like which power, there's all this stuff that anybody who's built a complicated system knows this is why it's complicated, but most people don't even think about it, right? So you have to have API calls for that. How we do clocking, how we do VDD setting, and then security, like what level of security do you care about here? Where is the encryption going to be? There are many issues that if you have APIs, then people can call them or not call them, depending upon what they want to do. But if you don't have them there, these devices will not work well. And then from a system issue is, like, what are the abstractions? People talk about chiplets, like what's the low-level interface, the wires, UCIe, all that kind of junk. Like, if I'm an application designer, I don't care about any of this stuff. What I care about is how do I get my data that's in my user space to my piece of hardware? And how do I do that effectively? How long does it take me to send a command? Like how do I send a command, right? Like we do mailbox. Like, there's lots of ways that we do things, but fundamentally it comes down to DMA or memory rights. Like, how do we abstract that in a way that a user application can get to the hardware and communicate with it? And we have to do that in a way that we can automatically generate the drivers for this piece of hardware. Because if it's in a normal operating system, it has to have drivers, it has to be protected, there's all this stuff that all has to be generated. And we need very efficient data transports. And how are we going to do that both in hardware, and how do we give access to it for software? I mean, there was some talks before about page faults in I/O devices. And the point is, you have this huge piece of hardware. You do not want it ever to wait for a page fault. So that means all the data that you're going to transfer in has to be locked in some way, so that when the DMA gets to it, it's actually there. And there's just a lot of all these things. There's a lot of details. I think we've been working on these issues for a long enough period of time. We have ideas on how to do this. Let's just try to codify them and not argue about whether this little thing is better than this little thing. Let's just get some base platform in there that we can start using. And finally, there's validation and debug. Now, one advantage of an app store is that when I write an app, I don't worry about whether all the other apps in the world can use my app. I just worry about whether my app works. So when I build a piece of hardware today, I have to worry about every crazy programmer that could ever exist. What could they do, and does my thing work? If I build a piece of hardware for my application, I care about, does it work for my application? And if it has a little funny things, I'll change the algorithm a little bit. So the validation is a little easier if I'm single use. Right? It's still not a trivial problem. I'm not saying it's not an important problem, but I can see a way that we can do validation in the app model. Okay? I do believe that you're connecting to a very complicated system that does weird things. So you will have to do debugging. And how do you provide that debugging interface to a person who's used to GDB or, take your favorite software development environment? And so we have to support source level debugging. And what does that look like? How do you do source level debugging when some of that source is implemented in hardware? I don't think it's impossible, but I think it's an interesting challenge. So let me end the talk by a plea. I hope I've convinced you that at least this is a possible idea. It might be a little crazy, but it's possible. Okay. The problem is there's sort of good news and bad news. And the good news and bad news is this is currently what a VC will call a $0 billion market. Okay. Which means that everything that you think you can make a lot of money on is being handled directly. What I'm trying to deal with is the tail. Right? The tail doesn't seem to have a lot of money in it. Okay. So the good news of that is that I don't have to worry about a company squishing this research effort. I don't think any rational company is going to do this. Okay? The bad news is, it says here, I don't know who's going to pay for it either. Right? So I do have a plan. Okay. The United States just started the CHIP Act, which is to basically reinvigorate semiconductor technology and design in the United States. There's a lot of money there. I don't need a lot of money. I just need a little bit of money. But I think with a little bit of money, we can convince some people who have platforms, because they've already got the platforms, to work with us to try to develop this API and to allow researchers across the country to play. I think it will take time and money to develop this interface. Well, I'm hoping that we can get some money from the CHIP Act to do that. Okay. So I'm talking to vendors, and I will say that many of the people who build these large platforms are interested in doing, are intrigued by it. I mean, they need to protect their platform. They don't want to get a black eye by people saying their platform doesn't work, blah, blah, blah. There's a lot of downside risk for them, so I understand. But I think we can convince people to play. I think the infrastructure for building chiplets to allow their base platform on their base substrate, which has chiplet interfaces, is already going to exist that we can leverage. So from the big costs, I think they're already done, and that we might have the ability, and we will have the ability to more easily put customized chiplets on platforms. That's part of the CHIPS Act already. What we need to do is rally the design community together to try to solve the problems that I addressed, so that we all can have students, or if you're a student, that you could, with your buddies, play 4 people over a quarter and come up with some design that you actually could fab to see if you can improve a base system that you really could use. I hope you join me. Thank you all for your attention.
So the first question I have is regarding, it sounds like you're suggesting to build an API-based accelerator, a collection of some kind of processor that seems to me similar to the idea of conservation force that has been. So I'm wondering if that's the stem or similar idea. And the second question is,
well, let's do one question at a time, because my memory's not that good. I'm getting old. I think the point is that the API is a software API. It is not actually for a piece of hardware. So the conservation cores were basically trying to take some applications, and then they had a set of tools to try to build something for that, right? So in that idea, there's some similarity. But remember, I'm thinking that this is a base system that already exists. The conservation cores were basically building the entire system. So I'm not doing that. And secondly, I think that the hardware that gets constructed is very different for each of the different applications. And again, in the conservation cores, they looked at a whole bunch of applications and tried to build an engine that worked on that whole bunch of applications. So I think there's differences on both those places. But there are many ideas in that thing, in that stuff that Mike Taylor did, that I think are really useful and interesting to look at.
The second question is, so this talk is about ASICs and a lot of wondering how do we position the future?
Yeah. So the question is, how does FPGAs fit into this whole vision? I think FPGAs are extremely useful in this vision because they are going to be the prototyping platform that we use to basically do some of this testing out. So I assume there will be a chiplet interface with an FPGA on it that you might be able to demonstrate some of your systems. I think part of the problem with FPGAs is that the programmable logic is very flexible, but it has a high energy and area overhead compared to an ASIC. And so FPGAs have been hardening various parts of their design to get around that. And again, I think that's very useful technology. It's a slightly different vantage point because I'm trying to build something that doesn't have that overhead, but does have the 3-month lead time for chip fabrication.
Actually, I was thinking about this data and how do you thinking about recycling programmable logic. But this vision of first I want to check it. And but the problem doesn't align very well with this vision of the app of Apple because the apps at the different levels are not inserted inside the hardware of the Apple chip. Here, we want something that is in the innards of the processor that operates and communicates and is part of the functionality of the processor.
So you're making an assumption that the changes will be made to the base core of the Apple processor. I'm not assuming that that's going to be possible in the first generation of this. I'm assuming that these were going to be distant accelerators, not things inserted into the processor. And so these accelerators are not going to change the memory system of the base platform. They are not going to change the processor of the base platform, because once you touch that, you basically own all the complexity of that processor, and the validation of that is nearly impossible. So again, we can talk about what we need to do for insertion and what we need to do ultimately, but for insertion, we are not going to touch any of those processors. You cannot touch a high performance processor core today and not think that you're going to spend $1 bazillion basically validating it. So don't do that.
Question: how do you manage the software elements, wireframes, and software usually can integrate hardware is usually like results, and software tends to adapt to what hardware provides. For example, if software got funding the platform is not that forward, that open, then it means the software goes over here, right? Hardware can see this plan, and then you adapt the hardware to the software code. So how do you prevent this kind of weird phenomenon evolving to a weird direction?
The acoustics are a little bad, so I'm not sure I got the whole thing, but I think software and hardware have different time frames. I agree with that. If I'm correct, and we can pull this off, the difference in time frames, hardware time frames will become much shorter to design. That's one thing. Second thing is, in my experience, software is not as soft as hardware is. It used to be people thought that you could, change software and you can't change hardware that much. In many projects I've been involved with, actually the hardware has to deal with certain characteristics of the software because the software can't change. Second thing is in software projects, you often use extensively libraries that are highly optimized. Those library interfaces don't change as rapidly as the software does. So one way of thinking about this is taking some of those libraries and hardening them. I mean, right, I'm gonna put something, when I harden something, I am gonna make it less changeable because it's gonna be deployed for a couple of years, right? So as an application designer, I care about what things are stable and what things are changing, and I will harden those things that I can harden, but not those things that are changing rapidly, right? So I'm not, again, I'm not in this thing gonna harden the entire algorithm because no software app designer would wanna do that. But I might take certain computations that I do and decide that those computations are stable enough that I want to harden those and get the performance advantage that I want. Am I answering your question? I can't tell. Okay.
Again, great talk. Thank you so much. I guess I follow your idea. Not open API, it's not open industry consulting, it's not open source. But people don't remember, but I asked you the open source hardware question. I think about another idea with you real quick. Because recently I learned this from Professor Ian Bucket. He's way to handing scale, and data bricks effort. I think maybe open source has its place. Here's the idea. Just follow what they have been doing. You start with open source, but actually there's always big ones behind open source, even if it looks like decentralized. And here is what they do. After they get the open source going, they start a startup. They have very strong leadership behind it, and then they get further funding from the corporate market. Public market is good idea. So the reason is, I think Ian said was because it's open source space, typically it can be the key is much higher in terms of investment. Would that solve the problem of funding and communication?
Well, so I'm not saying open source can't work. Like, what I'm saying is that when we talk about open source, we need to figure out a way that actually makes it successful. I'm happy to check with you after the talk about ways that we can make this work. I mean, I would love to have a vibrant open source hardware. That would be awesome, right? I'm not against it. I just right now, I haven't figured out how to do it. Right? So.
Eric Altman, IBM, great talk. I wondered about if you had more granularity on the types of software you expect. Startups, they're interested in time to market and having features, and performance is really secondary to most of the market. So do you see attracting those people or more legacy sort of software, somebody doing maybe the basics of web serving stuff with more legacy, maybe it's just early adopters.
So I think if you have an idea and you're just trying to push that idea out, as you say, what you're interested in getting it functionally out there. So I think those things aren't typically focused on performance initially. They're just interested in functionality and they'll use cloud or whatever resources they need. I think if we look at many of these applications that we're trying to deploy today, they are running into performance constraints if you want to distribute them, either because you're trying to do it in some sensing space. So you have an application. If a platform that you can buy today satisfies your application, you run with it and you will not ever want to do this. Okay? The point is, if there are many applications that are running into constraints, and I think in the future that will increase because the platforms are not improving in performance, and there'll be more people who are stymied by the ability to get the computing that they need on the platforms that they have. And it's those people or those groups that I think would want to use this. Now, is that a very big group right now? No. Do I think that group's going to grow in the future? Yes. So why don't we get the technology out there before the problem becomes huge? But I'm on a soapbox right now. I can't prove anything, but it seems right to me. What can I say?
Thank you. Hi, open question from Paris. The great talk in sujet vraiment implanting this platform, but through a PhD I studied security, and now I am more inquired about implementing accelerators and all the directly by users because they can interact. Do you think such an approach should is present the side effect of such accelerators to the users of the app system, or should just abandon showing this effect and just say that they should not expect security from this type of platform?
Did you understand? Let me ask you. The acoustics up here are really bad because the speakers are all going backwards. So I'll find you afterwards.
Thank you. Very grateful. I see the last idea of making are available for the community or for everybody. But in the end, you also need to manufacture it. So how do you see how to make manufacturing cheap and simple? Because I mean, even as a university now, getting access to the latest technologies and also paying for this is not that easy. So how would you do this for the millions of people?
Right. So the question is really about how do you make the technology available? I will say that because technology scaling is giving you less and less benefit, I'm not assuming the chiplets are going to be in the latest and greatest technology because I don't think it matters that much. So it's going to be it's some older technology, maybe 16, maybe 22, something like that, which is, and I don't think these chips are necessarily going to be huge. The chiplets are going to be huge. So already in shuttle surfaces, you can get those kind of chips for tens of thousands of dollars. And I think there is already within the United States a desire to make some shuttle services available for experimental stuff. So again, it's going to cost some money to do that, but it's not the very large cost that people talk about, like the $10 million for a mass set, because it's going to be in a multi-project wafer. So you're going to do all those things. Do I think if this turns out to be successful, that people will then innovate on how to reduce that cost and maybe time? Yeah, maybe. But I think even today, I can see a thing where the total cost of doing this is on the order of 100K-ish. And there are various agencies I can think of that will support this kind of infrastructure. But it's a good question. I don't know.